to welcome everyone. My name is Rebecca Lowe. I'm the Adult Program Coordinator at the Lewis Public Library. Thank you for joining us this evening. So welcome to our series, Science and Society. See, I can hear somebody who is unmuted, so I'm going to go ahead and mute you. Please remember to keep yourself muted. Thank you. So welcome to our series, Science and Society, Making Sense of the World Around Us. This lecture series is co-organized and moderated by Fred Dilla, Executive Director Emeritus of the American Institute of Physics and author of Scientific Journeys, Linda Dilla, former Public Information Officer at the Jefferson Laboratory and the U.S. Department of Energy, and Colin Norman, the former news editor at Science. So with that, I would like to turn the floor over to Linda. Thank you.
Good evening, everybody. I get the honor of introducing James because I've known him the longest. We met back in the 90s when we were both at Jefferson Lab in some way or another. And James went off on a career that ended up in DC, and I and Fred followed him up there eventually. So he ended up for quite a long time at the American Physical Society. And after that, he started just being a science journalist and has written for Scientific American, New Science, Popular Science, the Washington Post, you name it. He's written it and has created professional societies associated with science writing, and now is under contract to write more books, and actually is married to another science writer that all of us know. So it's science writing in the house tonight. And I want James to tell us about the most mysterious particle in the universe. And he actually has a family connection to that I hope he gets into as the talk goes on. So welcome, sir.
Thank you. Yeah, I'm thrilled to be here. It's a terrific program we all are running, and I'm glad I could be the final
finale.
Speaker. That's right, the finale. So I'm going to go ahead and share my screen, if that's good. Oh, there we go. And we start. Okay, so how's that look? Is that good, everybody? Yeah, so I've written recently with my good friend and former boss, Alan Chodos. We wrote a book called The Ghost Particle, which is it's named the ghost particle because it was such a mysterious particle to begin with. One thing that occurred to me in giving this talk is that not everybody necessarily walks into a talk like this understanding what a neutrino is. So if you're not a particle physicist, you might be wondering what is a neutrino exactly. If you do happen to be a neutrino particle physicist or particle physicist, you might be wondering, what is a neutrino exactly? And the reason that I say that is because the neutrino, there's some things that we definitely know about neutrinos. We know that they are elementary particles. So if you're familiar with electrons and protons and neutrons, it's another one of the elementary particles. Along with the photon has no mass. The neutrino has very low mass in comparison to the other particles. There are other things we know about it as well, and I'm not going to go through in detail all of these. But one reason I wanted to point out to you that this is what we know is because there's a great deal that even physicists don't know. This is a list of things on the right that are still mysterious. We don't know exactly how much they weigh. We don't know how they respond to magnetic fields. We don't know about the three flavors, which are listed on the left. There's a mention of the three flavors. We don't know how the mass is distributed between those. We don't know why they have mass. Other particles have mass in part due to the Higgs boson. That is not the reason neutrinos have mass. We don't know if they're their own antiparticles like photons are, or if they're not like other elementary particles. We don't know if there are more flavors of neutrinos. And we don't know if they can decay into something else. And there's even more that we don't know. So if you've never heard of neutrinos before and you walked into this room, a particle physicist only knows about 40% more about neutrinos than you know at this very moment. They're that mysterious. And that's why I consider them to be the most mysterious particles known in the universe. If there are more mysterious particles, we haven't found them yet. Is there a way to get rid of this little bar at the top? Because I can't see my screen entirely. Rebecca, I don't know if there's a
you might be, we can't see it, but if it's the taskbar, you can always grab it and drag it to another area, if that would help.
Okay, I'll try to do, oh, there we go, because I can't read my own screen. Okay, so the question, now that we have established that neutrinos are these very light elementary particles and are mostly mysterious, the question that you might be asking is, where do they come from? And in fact, okay, there we go. Many of them come from stars, like our sun. A lot of the ones that are passing through you at this very moment come from the sun. They also come from cosmic ray particles that hit the atmosphere, usually protons or other sorts of particles that hit the atmosphere and create a huge shower of particles, including neutrinos. These are called atmospheric neutrinos. A lot of them are produced in nuclear reactors and other nuclear processes, like nuclear weapons, for instance. Many are produced through the natural decay of particles of elements inside the Earth, uranium and thorium and things like that. So you have neutrinos, geoneutrinos coming up from the Earth. And there's also neutrinos coming out of my watch. I have this watch which produces about 5 million neutrinos a second. And that's because that watch is illuminated using tritium gas. And when the tritium gas breaks down, it produces two things. It produces an electron and it produces a neutrino. The electron hits the phosphorescent material inside the tubes and makes it glow. The neutrinos come shooting straight out. So if you have a watch like mine, you're being bathed in about 5 million neutrinos per second just from that watch. There are lots of neutrinos in the room with you right now. Many of them are coming straight from the sun. A normal size, average size human being could experience about 100 trillion solar neutrinos passing through them every second of their life, coming straight from the sun. I asked artificial intelligence artists to illustrate what this might look like, and that's not really bad. The amount of if neutrinos were the size of a grain of sand, they would fill up about 6 dump trucks worth of sand every second. And so that's what neutrino interprets, or artificial intelligence interprets that to look like. There are, at any given second, any given moment, there are about 15 neutrinos inside your body, and there's 300 to 500 of them in your fingertip alone. Okay, come on. There we go. They are mostly harmless. They're like most things in life. There are some caveats to that. As far as we can tell, you're probably not going to be injured by a neutrino. The chances in your entire life, if you live to be about 70 years old, of a neutrino stopping somewhere in your body is about you have about 2 of them will likely stop somewhere in your body during your lifetime. It'll change an element, say argon or some other atom inside your body, into another type of atom, but you won't notice because you're made up of trillions and trillions of other atoms. One thing that we try to address in this book is how neutrinos can answer some of the biggest questions in the universe, that we know of in the universe, including some that go way back to early stages of physics in the 1900s. And one of them was a big issue for Lisa Meitner, who was concerned about some strange behavior that was going on with radiation. And that is, some atoms that exist in nature decay. That is, they change from one type to another by emitting what they considered what they believed was called a beta particle, which is actually, in fact, an electron. So a neutron in an atom will sometimes break down and turn into a proton, and in the process, it emits an electron. The problem is that those beta particles, those electrons, can come out with a variety of energies. And you would normally expect, if you have a particle that breaks down and shoots off from an atom, that it will have a specific energy, and it doesn't, in fact. They measured it. Lisa Meitner was one of the people that measured it and found that it comes out with a variety of energies. And this was very disturbing to Niels Bohr, because Niels Bohr noted that if you have electrons coming out of atoms at different energies, you could always play this little game. You could look at, I should back up and say the other possibility is that an electron can go into an atom and convert a proton back into a neutron. This runs both ways. And in both cases, the variety of energies that are involved is a spectrum. It's not a specific energy. And that means you can play this game that he proposed, and that is you could take the high energy electrons, and that's easy enough to separate out, you could use them to run a motor. And then now that you've sucked out some of their energy, you could send it back to an atom to restore it to the status that it was in before it had a beta decay, an electron decay initially. And if you can do that, that means you can now essentially suck energy from nowhere. You could make what Niels Bohr believed to be a perpetual motion machine if this was true. And that's a real problem because perpetual motion machines and free energy machines are they're anathema to physicists. They hate the idea of them. They really shouldn't exist. And it was, for some people, it was an argument as to why we could not have beta decay. There was something wrong with beta decay, and there was something wrong with thermodynamics. So Wolfgang Pauli looked at the situation and thought, well, maybe there's a solution. And his solution was that there was an invisible particle that was accompanying the electron. And now if you add up the energy of that invisible particle and the electron, you end up with the same amount of energy being produced each time. And because it produces the same amount of energy, you can't take an energetic, a low energy electron and put it into an atom and get back to the same state. You've lost some energy. And so this saves thermodynamics, assuming that this invisible particle exists. And he called that particle he called it the neutron, but because that name was later taken by another particle that most of us know about, it was changed to neutrino. I believe that was Enrico Fermi that called it neutrino, which means the little neutral one. The problem is, let me slide my little bar up here. There was no sign of these things in any experiments that anyone had done. And so Pauli had to go a little further. He had to say, not only did this particle exist, but it was fundamentally undetectable. And this was something that actually disturbed him and a lot of other people in physics at the time. He said that it was, goodness, this bar is really annoying. Let's see. It's an elementary particle. It had extremely low mass and no electric charge, because otherwise you would detect it. Spin a half, which was necessary to balance the characteristics of the emitted electron, and that it was inherently undetectable. Pauli was so disturbed by this that he's often quoted as saying, I have done a terrible thing today. I've suggested something which can never be verified experimentally. And he was very sheepish about that. But Wolfgang Pauli was Niels Bohr was so disturbed by that he said that he would refuse to accept the possibility of neutrinos as proposed by Pauli, to the extent that he was willing to essentially jettison thermodynamics. He was willing to take thermodynamics, which had been built up and been proven to be one of the most successful ideas of the day, and he preferred to throw that away and assume that we could have perpetual motion machines rather than accept the possibility that neutrinos could exist. Hans Bethe, who was another leading physicist of the time and helped develop the nuclear weapons at the Manhattan Project, among other things, decided to do a calculation to estimate how could you detect a neutrino? What are the chances that you could detect a neutrino with any means whatsoever? Oops. And he estimated in a paper that he published in Nature that if a bunch of neutrinos were going through the Earth, the chances that a single one would ever stop anywhere in the Earth was about, I think I have about 1 trillion to 1. And he ended his paper by noting that you can conclude that there's essentially no way of observing a neutrino with any conceivable experiment. So that didn't stop people from attempting. Most people, a lot of physicists of the day were convinced they exist, so they started to look for them in conventional ways that people had looked for other particles, including bubble chambers. James Chadwick did that at Cavendish Lab. There was an experiment done in the Holborn Station in England, where they attempted to look for neutrinos under the assumption that they had a large magnetic interaction, and that was a failure. And Horace Crane at the University of Michigan decided to look inside about a 2-pound bag of salt. He put a neutrino emitter, a beta particle emitter inside a bag of salt. He looked for the neutrinos to cause interactions, and he could chemically separate those out. He did not find any. And in fact, it wasn't a bad idea for an experiment, but he would have needed about 1 trillion times more salt in order to detect a single interaction. So the question is, do we just take it on faith, or is there a way to find neutrinos? And there are some things that you can do to increase your chances. You could make much bigger detectors. The Earth is large enough that there are interactions in it on occasion with neutrinos coming from the sun. You could do much longer duration experiments where you look at, for instance, a bag of salt for many trillions of years, or a large bag of salt for several years. Or you could look for much more intense neutrino sources. And as it turned out, that was the third option, was the one that was the first approach to finding neutrinos. And it was done by Fred Reines and Clyde Cowan of Los Alamos National Laboratory in New Mexico. Their initial proposal, since they had access to the programs to develop nuclear weapons, was to actually build a detector and place it in a hole close to a nuclear detonation. Yeah. So they had, and they acquired funding for this. They dug a tunnel next to about 137 feet away from a nuclear test. They built a detector the size of a school bus that they were going to drop inside a vacuum inside this tunnel when they did a test in that vicinity. And then the flux of neutrinos going by would, because it was so intense, these are the most intense sources of neutrinos on this planet. It's on the order of trillions of times what you get from the sun. That flux would have been enough that they would have expected to see a handful of detections inside this detector. And then they would go after the detonation went off, collect this detector from the bottom of the tunnel, which was lined with feathers and foam to prevent it from being destroyed, and pull it up and look for signs of neutrinos. It turns out that they didn't have to do such a dramatic thing. They also, as part of the nuclear weapons program, they had access to the Savannah River nuclear site in Aiken, South Carolina, where radioactive material for nuclear weapons was being made, but it required running nuclear reactors that produced huge fluxes of neutrinos, about 50 trillion neutrinos per square centimeter per second. They counted in their final attempt and successful attempt to look for neutrinos, they counted about 3 neutrinos an hour, and they saved physics, and Bohr was okay with that. So he didn't have to jettison thermodynamics after all. So the next big question that came about historically is, what's going on with the sun? There was a puzzle at the time. Now that they had determined through the experiments of Cowan and Reines that neutrinos existed, there was an expectation that neutrinos should be coming from the sun. And in fact, they are coming from the sun. The neutrinos are produced in fusion reactions at the core of the sun, along with the light and the heat that we experience. Now, light, because of the plasma gas the sun is made of, when the light is produced, when the heat, the gamma rays are produced at the core of the sun, it takes a long time for these photons to rattle out. Essentially, it takes about 200,000 years for light to escape from the sun once it's made in the core. Neutrinos, on the other hand, because they interact very weakly with anything at all, escape almost instantaneously. So they take roughly 8 minutes or so to make it to the Earth, while the light that's produced at the same time will take hundreds of thousands of years. So sunlight is old, and neutrinos are quite essentially offer a real-time look at the heart of the sun. So the problem was when John Bacall and suddenly his name escapes me, his colleague, two physicists decided to look for these neutrinos coming from the sun. They found that 2/3 of the neutrinos were missing. And this was a huge problem because Hans Bethe and other people at the time had come up with a very good model for how the sun works. And if you're missing 2/3 of the neutrinos, that means that you have some kind of a problem. One problem is we don't really understand solar fusion, and that seemed unlikely at the time because their models were quite good. So they seemed to predict everything else about the sun very well. Another possibility is that the sun wasn't powered by fusion at all, but instead was run by a black hole somewhere at the center that was consuming matter and radiating energy at its edge as it did. One other possibility that was raised in the literature by a number of people is that the sun is simply dead. It had stopped producing fusion. And because of this long delay in the time that it takes for photons to get out, we weren't yet aware. And it could be another tens to hundreds of thousands of years before we would see the sun actually starting to power down. And the final possibility was that there was something wrong with neutrinos as we understood them. And you can probably guess that these little guys, illustrated by the stuffies that you can buy online, neutrinos were in fact the problem. And the problem stems from the fact that neutrinos are unusual particles. Unlike any other particle, they can change identity as they're moving through space. This is called neutrino oscillations. In this case, this shows an electron neutrino produced in the core of the sun as it converts into a muon neutrino and then into a tau neutrino. So and this is probably, I would say this is the most challenging part of this presentation, so bear with me on this part. One reason, or the reason that neutrinos change what we call flavors from the electron to the muon to the tau neutrino and back again cyclically, is that they're made of three parts that are known as mass states. So I know this may sound a little obscure, but if you imagine that the electron neutrino is made of mostly mass state 1 and a little bit of 2 and a tiny bit of 3. Then a muon neutrino is made of a different mixture, which is more of the 3 and less of the 1. And the tau neutrino is made of mostly 3 and less of the other 2. Now this may seem like just taking one strange mystery and replacing it with another. But the fact is that as the neutrinos move, these mass states are different masses and they move at different rates. And you end up with different overlaps of these mass states as they get to you. I was trying to figure out a way to illustrate that. So my daughter helped me make these three blobs of clay, which represent the three mass states. And it's reasonably analogous in the sense that two of these mass states are about the same and one is much larger. And as you saw in the previous slide, the third one, which we painted purple, we call mass state 3. We know it's very different from mass state 1 and 2. It could be much lighter or it could be much heavier. For the purposes of illustration, we propose that it's heavier. And now this shows how as a neutrino is moving through space, it has a certain proportion in each of the mass states. And she just put it in a state that looks very much like it was loaded with mass state 3. And you can see that the energy from that one swinging is being transferred to the other two. Now, of course, these aren't neutrinos, but the math that describes how this energy flows back and forth is very similar mathematically to what's actually going on with neutrinos. And so you can see now the mass state 3 is starting to lose energy, and this is transforming essentially more into an electron or a muon neutrino that are heavy in the other mass states. So mathematically, you have to trust me on that, but it essentially illustrates how neutrinos oscillate as they move through space. And these sorts of oscillations were confirmed finally in 1998. And as a result, solar physics, as described by people like Hans Bethe, was saved. So let's move on to the next big cosmic question that neutrinos can help with. And that is, how did everything get here? Right now, neutrinos can't give us the answer just yet. We can't look at neutrinos and put together some sort of theoretical explanation as to why they had anything to do with the beginning of the universe, but they can do something else. And that is, if you look at this cartoon that essentially shows the universe we live in, there was a big bang, there was a period of inflation, as at least canonically, that's what people believe today. And the universe then expanded very rapidly and now is continuing to expand. And we are at that point in the universe, so the little yellow mark. So there was something interesting that happened at the beginning, we call the Big Bang, and then we can't really see back past what is called the cosmic microwave background. Beyond that, everything is opaque. The universe was very hot. It was Everything was ionized and light didn't move through it very well. So the farthest we can see back in the universe with anything that involves light is to the cosmic microwave background. But that leaves this mysterious period right there between the Big Bang and the cosmic microwave background. And that's, in the grand scheme of things, that's a small portion of time, but it's 375,000 years or so. Neutrinos were made, however, at the very beginning with the Big Bang, about a second after the Big Bang. And that means that if we could look at neutrinos, if we could see the neutrinos coming from the Big Bang, they could reveal what's going on in that 375,000 years that is completely invisible to us right now. So currently, these neutrinos are very, very cold because they've been in the universe since then, and they've been expanding, they've been cooling down as the universe expands. We don't have a method to detect these neutrinos just yet, but there are schemes in place, and we could discuss those if anybody has a question about them, to potentially detect these neutrinos, which means that they could be the one way that we could produce essentially images of the universe during that 375,000 years of that the universe was opaque to us. The only other thing that could see back that far would be gravitational waves, and that's something that hopefully we'll get as well. But neutrinos are the one thing that can produce something essentially like an image of the beginning of the universe. We could hear it essentially with gravitational waves. Another big cosmic question, let me see, I hope I'm actually going a little fast on this, but is why is anything still here? So neutrinos can give us an idea of what the universe looked like at the very beginning, or close to the very beginning, at least up to a second. But then the problem is, when the Big Bang happened, energy turned into matter and antimatter. And it should have turned into matter and antimatter in exactly equal proportions. When you take antimatter and matter and you add them together, you get energy. So the expectation would be that there should be no matter or antimatter left in the universe at all. You would expect all of the matter and all of the antimatter to eventually find each other and annihilate and create energy. But in fact, we're still here. And part of this can be explained by Ettore Majorana, who proposed a mechanism involving neutrinos and other particles eventually that would account for the fact that not everything annihilated. Some stuff is left over in the universe. That's why we're here talking about neutrinos at all. So his proposal was that a neutrino not only can they oscillate among different flavors, they can actually, he suggested, oscillate between their matter and antimatter version. In this case, the yellow neutrino represents a matter version, and the gray one represents the antimatter version of a neutrino. Neutrinos come in antineutrinos, and neutrinos, just like electrons, come in anti versions called positrons, and electrons and protons can also come in their antimatter partners. So his proposal was that when there is a beta decay, when a particle emits an electron and a neutrino, there has to be a balance of matter and antimatter. Every time a matter particle is produced, an antimatter particle is produced. And in this, there are some cases where atoms will produce two beta particles, two electrons at the same time, along with their accompanying neutrino antimatter partners. When Majorana proposed that one of those neutrinos can actually convert into its antimatter partner, and that means that there's a small chance that the matter and antimatter neutrinos could then annihilate before we see them. And the end result is that we see an atom producing two additional matter particles. So the number of matter particles in the universe increases by 2 with one of these neutrinoless double beta decays, is what it's called. And once that antimatter-matter imbalance is created in something like a neutrino, you now have a net change in the universe, and you can explain through other mechanisms how there is this sort of residual amount of matter that makes us and stars and the universe, everything we see in the universe, possible. So it might essentially account for why we exist at all. And if so, we and all of our stuff are saved by neutrinos. I should slow down a little bit. I'm going so fast. So here we are to what I call the big cosmic question. And that is, where is everybody? It might not seem like at first glance that neutrinos could address such a question. At this point, we've been using things like the Arecibo radio antenna to look for signs of aliens in space. But there are good reasons to suspect that things like this, which is a neutrino detector at Fermilab, might be a better option. And the reason I mention that is that people have done experiments where they've shown that you can transmit messages with neutrinos. They essentially took the particle detector system at Fermilab, where they can produce neutrinos in an accelerator. They encoded a brief message that read neutrino, and they sent it through about 270 meters of rock to show that you could convert your neutrino accelerator, your neutrino source, into a message-carrying beam of neutrinos. If you imagine that aliens somewhere in the universe wanted to speak to us, they could do the same thing. They would have to build an enormous neutrino source in order to do that. And the one way you can tell this is huge is because at the far right of this diagram is an example of the Earth, showing how large, how long your accelerator would have to be. It would have to be enormous to produce the energies that would be appropriate for sending neutrinos across the galaxies and across the universe to communicate with us. That's far beyond the capabilities that we have currently. But if you imagine that aliens could do such a thing, they could then send neutrinos through essentially all of the stuff, all of the dust lying between us and them, which makes up the galaxies in the universe. Right now, if you were an alien, you were trying to send a message with optical signals. Here's an image of the Milky Way galaxy. You can see that a lot of the message would be obscured by dust in the galaxy. You could use higher energy light, like gamma rays, but even then, you're going to have some scattering. You're going to have distortion in images. Neutrinos, we know, can get to us undistorted, and one reason that we know that is that physicists at IceCube, the neutrino detector in the Antarctic, have produced the first ever image of the Milky Way galaxy using neutrinos. They've looked at a type of scattering which they had been ignoring for some time because they didn't think there was information encoded in it. They applied an artificial intelligence analysis to find that they could produce these rough images of the Milky Way. It's a very crude image in comparison to the other ones because we just have these crude detectors at the moment, and they're becoming more sophisticated. But we can, in fact, at some point anticipate that a source of neutrinos will produce a signal that comes straight to us without essentially being absorbed by the intervening material. So it might be a really good way to send a message over a great distance. One of the benefits of that is that you could precisely target your images. You could point it, you want to talk to somebody at a specific place, you point your neutrino beam at them, you don't have to make a huge bright light. You can instead just pick who you want to talk to and send your beam. The nice thing about that, some people have proposed, is that if you wanted to talk to somebody, you're not sure that they're hostile aliens somewhere else that you fear might overhear and your message and come and eat you or do something insidious. You could avoid alerting anyone else because you have to be in the line of the beam in order to see it. And of course, when you know who you want to talk to and you know where they are and you point a beam at them, you can do it much more efficiently than you would if you were to just make a bright light. There is, however, another approach that some physicists at the University of Hawaii have proposed, and that is that throughout the galaxy and throughout the universe, there are these variable stars known as Cepheids. And Cepheids are, it turns out, on the verge of stability, which means they go off every once in a while with a bright pulse. And what causes that bright pulse is this unstable behavior, which means you can trigger it essentially by doing what these physicists proposed would be using neutrino beam ticklers. So the stars are mostly opaque to neutrinos, But when you have a star like a Cepheid that's on the verge of instability, potentially you could use a neutrino beam to fire at it slightly off center, which would cause it to flash at a predictable rate. So you could trigger Cepheid bursts at whatever rate you choose if you had the technology to do this. And John Learned and his colleagues at the University of Hawaii have proposed that, in effect, you could make the largest internet communication scheme conceivable. They call it the Cepheid Galactic Internet. And in effect, you could do the same thing that you do with your router at home to transmit information, and aliens could, if they wanted to, they could send us messages by tickling these Cepheid stars. And in fact, John Learned and his colleagues, Anthony Z, have proposed and have searched for signals in Cepheid variable flashing in years past. So far, there's no indication that there is a Cepheid galactic internet, but it's nice to know that there are at least people looking for them. So in conclusion, I mean, this is not everything that you can do with neutrinos, and not everything that neutrinos can tell us. There are many issues that I have glossed over or ignored in this case, but at least when it comes to the cosmic issues, why are neutrinos important? And that's a question that I get a lot. And one is, they help us understand why radiation happens at all. They help us understand why the sun shines, why it works at all. And they showed us why, potentially at least, that we could look and see the very first moments of our existence as a universe with neutrinos, and they could explain why any of us are still here. And finally, although it seems unlikely, it has been proposed, at least since the very beginning of neutrino research, that they may make the best way to communicate with aliens, or with aliens communicating with us, provided we are looking for other civilizations that have the capability to detect and create neutrinos. So I know I was excited and rushed through that, but I wanted to point out that these and a lot of other issues are described in our book Ghost Particle, which I wrote with my good friend Alan Chodos, who's also a friend of Linda and Fred.
Yep.
And I wanted to wrap it up with this little poem that was written by Fred Rhinus, who was one of the co-discoverers of the neutrino. This is a toast that he wrote. Here, and I'll just read it to you. Here's to Wolfgang Pauli, who made a funny joke. Here's to the great Enrico, who then of weakness spoke. Here's to all those gathered to celebrate the fruits of all the patient workers who followed those astutes. Here's to the proposition that we shall meet again, and here's to the fond hope that the sun will shine till then. And finally, I will say, coincidentally, our book was chosen today by Science News Magazine as one of the 12 best science books of 2023.
Wow, congratulations.
Thank you.
James, thank you for a very enlightening talk about a mysterious particle, and congratulations on that book. There's a question or two from the audience they would want to bring up, but first I want you to, since you've alluded to 4 cosmic questions that the almost century of study of neutrinos have helped divulge answers to, tell us about your personal connection, your grandfather.
Oh yeah, right. I should have mentioned that when he came up. I am the grandson of Clyde Cowan, who was one of the 2 physicists who first detected the neutrino at Los Alamos. Clyde unfortunately passed away in 1976. Fred later won the Nobel Prize, I want to say 1996, for discovery of the neutrino. Had my grandfather been around, I suspect he would have shared in that prize.
That's right.
But it was delightful to see Fred Rhinus receive it in 96.
Well, while you're on that slide right there, there's a question from someone that you probably know, Anne Finkbeiner, who's a loyal listener to our Science and Society series. And she asks, if neutrinos rarely interact with anything, which you showed us, what would a cosmic neutrino background show that's interesting? Like, they really don't affect anything. And so what would you learn about how they might get through that early part of the universe?
Well, and so if you look at this diagram, and there's that layer that's called the cosmic microwave background, that's actually very smooth, right? The energy fluctuation in the cosmic microwave background is very small, but the detail you see in it shows that there are these fluctuations that late in the universe. If we were to look at the neutrinos coming from earlier, we could see all the way back and look at this evolution from the singularity, which we think was at the beginning of the universe, to the cosmic microwave background, and understand where that structure came from, because that structure later seeded the entire structure of the universe as we see it today. So there are proposals about what the Big Bang was. There are other people that say there was not in fact a Big Bang at all, but it was a big bounce, and that there were there's this repeating cycle of universes being created and destroyed. Those are the sorts of things that we could, with neutrinos, look back to the very first second of the universe and see that development and understand what happened to get to the cosmic microwave background, which is one of the most important structures that we look at in astronomy, that helps us to understand where the universe came from and how it got to the condition that it's in right now.
Thanks, James. One of the other questions that probably some of our viewers and listeners are wondering about, you've certainly made it quite clear that neutrinos are everywhere, trillions going through us right now, from sun, from cosmic rays, from local radioactivity. But I'd like you to spend a minute or two describing how difficult it was to detect these things. There's a hint of that with your grandfather's experiment with a vacuum tunnel dropping a detector the size of a bus down to a bed of feathers next to an exploding nuclear bomb. But say a little bit about the detectors that are used now, like IceCube and the ones under Gran Sasso and the ones under a big mountain in Japan, that these are not simple little lab experiments. Tell us about the scale of detectors that are needed to find these ghost particles.
Yeah, certainly the largest one right now is IceCube. And in trying to explain, my daughters once asked me how big it was. And I said, as I mentioned in the talk, that if you live to be 70 years old, the chances that a neutrino will stop somewhere in your body are that it'll happen once or twice in your entire lifetime. There are many, many detections in IceCube. And so you might wonder how, if it's so rare that it would happen in somebody the size of a human, why does it happen so often in IceCube? And that is because if you add up the mass of IceCube, which is water, humans are mostly water, there's roughly twice as much water mass in this IceCube detector, which is a cubic kilometer, a kilometer on a side. There's twice as much mass as there is of all the human beings on the planet added together. If all of us stood side to side, touching inside a volume, we would only fill up half of IceCube. That's how big it is. And they do detect many, many, I think hundreds of thousands of interactions a year. And if you take all of humanity and add our weight up together and multiply that by 2 detections per lifetime, that's roughly how many you would expect from a detector made up of all the humans on the planet. And there are plans to make bigger detectors than that as well. Now, they've also made really small ones recently, which is something we get into a whole chapter in the book, coherent neutrino scattering that involves neutrinos essentially. The analogy that the people have developed have said it's a little like throwing a ping pong ball at a bowling ball. You can see the motion of the bowling ball. You need a really good detector to see it, but now you can make neutrino detectors small enough to fit on a desktop, in effect, using this other detection scheme. There are reasons why it's not really useful for many of the things we use neutrinos for, but it does show that you can build a huge range of sizes of detectors now, which we had no idea when Pauli first came out and said they're just absolutely undetectable.
You've done a great job, even though you had to get probably more technical than most of our audience, of showing how neutrinos have helped solve 4 big mysteries: the nature of radioactive decay, how does energy come out of the sun, how did our universe evolve, and why are we here, matter versus antimatter. I want you to touch a bit on the occasional thoughts that physicists and others have had for practical use of neutrinos. For example, well, I'll let you answer that question. Those that have tried to use neutrinos for something practical, not just to answer a mysterious question in physics.
Yeah. Well, certainly the one of the first things that people proposed was that you could use neutrinos to do things like look for nuclear submarines. So a nuclear submarine runs on fission. Fission produces neutrinos, and that's the one thing that they can't stop inside a submarine. It turns out that it's really difficult to detect those. You can do it with a detector about the size of the ones that we use for contemporary research, ones the size of football stadiums, but those aren't very practical for looking for submarines. So it doesn't end up being very handy. But there are people at the University of, Virginia Tech, who are proposing truck-sized detectors that you could drive up to a nuclear reactor, and you can look at the neutrino flux and tell whether people are using the nuclear reactor just for energy production, or if they might be using it to produce material for nuclear weapons. So it might be handy, say, in a place in some country, which I'm not going to name any, which may not want to give us access to their reactors, to see if they're being good when it comes to what they're doing with their reactors. You can also use it to monitor nuclear waste underground. So because you now have time and you have access, you can make sure that your nuclear waste storage facilities haven't been molested, they're not leaking, because you can put a truck-sized detector near one and keep an eye on what's going on with your waste. And those are, interesting, but the ones that I find most interesting are the potential to use neutrinos to do essentially X-ray the planet. So the neutrinos that I mentioned coming at the very beginning that come from the Earth, geoneutrinos, they come from nuclear material scattered throughout the crust and the core of the planet. People have already used neutrinos to get an estimate of the distribution, not very high resolution, but potentially when we have better neutrino detectors, we can take an image of the inside of the Earth in ways that we can't do with anything else. Right now, geophysicists use essentially sound waves passing through the Earth in order to see what's going on. When we have better detectors, we'll be able to get much more high resolution images of what's going on at the center of the Earth. So it's really the only radiation that can pass through the Earth. Otherwise, you need to use sound, essentially sound vibrations, to look inside the Earth. So it's going to revolutionize, I think, geophysics.
Well, that's good. I hope ExxonMobil is listening to you about this.
Yeah, there was actually an article in Physics Today, not in the 70s, that Sheldon Glashow wrote with some other people, proposing making a particle accelerator that created neutrinos that they could fire through the Earth to look for oil. And he's since said, nobody's going to look for oil anymore. We have to do other things. But you could essentially make a scanner that you could scan the planet with neutrinos and look for things like oil deposits, but also to study the Earth.
That's a good question from Colin.
Yeah. So our colleague Colin Norman has a question. You mentioned the very minute mass that neutrinos, their various flavors, have, and we still don't really understand what the mass is and the mass oscillations and how small it is and how it got there. So what are the best inclinations at the moment of where the mass of a neutrino comes from? Because we have a Nobel Prize for the discovery of the Higgs boson a decade ago that gave us the reason for every other particle having mass. So what's this mystery about?
I think that's one of the biggest puzzles. I mean, certainly we need to figure out how much mass they actually have to hone in on that. Some people, Alan has, for instance, has suggested in our book that there may be some coupling to a Higgs-like thing. There's another thing that we could look for, but at this point, all we know is the upper mass is upper limit of the mass. I think is on the order of 0.8 of an electron volt, and it may be much smaller. And the smaller it is, the more puzzling it gets as to where the mass might come from. So I think I don't know I'd have to stop and maybe even ask Alan what the various proposals are. But I think that we're so early in understanding the source of the mass. I mean, there is also the possibility that there are some very heavy neutrinos, so heavy that we can't produce them yet in reactors or accelerators, that would explain why the neutrino has a small mass. But I don't know that it explains the mechanism, other than saying that there seems to be potentially a very heavy one that could explain why the very light ones exist.
We're going to wrap it up with one more question. It's a question again from one of our loyal listeners, Linda Palmer, who likes to ask this question for anyone talking about astrophysics. And since you're a heralded science writer, we'll pitch this one to you. She says, well, what happened before the Big Bang? It's good you have this one up on the screen.
Yeah. I recently wrote an article for Scientific American about that. There are people who propose that loop quantum gravity, an area of this attempting to reconcile gravity and quantum mechanics, propose that what happened before the Big Bang was another universe that crunched down, and we're in this perpetually bouncing cycle.
Going from the big crunch to the Big Bang.
That's right. You have to do a lot of exercise to say how would our universe crunch, because our universe is in fact expanding. So how would it ever crunch and continue the cycle? There are contrived explanations as to how this might happen. But I think really, if you go with the canonical explanation that there was a Big Bang, the sky's the limit. It's wide open as to what could have caused it. I saw a talk at the Royal Institution where they proposed that we're actually in a black hole from another universe. That seems a little implausible to me, but it's a nice story. But unfortunately, nobody knows. And neutrinos may help us get closer to answering that question.
No, it's a good answer that physicists can't explain everything. Okay, we're still working at it. We're going to have plenty of rich problems to work on as physicists and even retired physicists. So, James, we're going to turn it back to our moderator, and we'll ask everyone to thank you for your fascinating talk. But before we do that, I want to remind everyone that we just finished our fall series. And as Rebecca mentioned, we are just about to announce the spring series, and it will again begin with Tim Appenzeller, the current editor of news for Science Magazine, and he will discuss the great breakthroughs of science in 2023, which won't be announced until a couple of weeks from now. And those of you who have tuned into this series for the last 4 years know that that's our kickoff talk for the year. So that'll be on the second Tuesday of January. So Rebecca, can we turn it over to you?
Yes. So I just want to remind everyone that there's a book for sale, a book tied to this event. So if you would like to purchase a copy, I've put the link to the sales through Browse About Books into the chat. And also you can borrow a copy through the Delaware Library System. So both those links are in the chat. So as is our custom, folks are welcome to unmute themselves and applaud and say thank you. So feel free to do that. So thank you.
Thank you.
Yeah.
Thank you.
Thank
Thank
you.
you. Good talk.
Thank you. Thanks. Lightning.
It's a pleasure. Thank you all for inviting me.
Thanks, James. Looking forward to seeing more of your articles published every single
you.
day.
Excellent.
All
Thanks so
right,
much.
everyone. Thank you so much for joining us, and we look forward to seeing you in the new year, and we hope everyone has a happy holiday.